I'm going to talk about the application of planning to stream processing. This is the work that we've been doing at IBM research. So this work combines several prior works, in particular the work that's going on at IBM on distributed stream processing, the work that we've done in our group at IBM Research on Cascade and Mario, the projects for composing stream processing applications automatically, and the work that Shirin Sarabi, the first author of this paper, has done at the University of Toronto before joining our group on HTN Plan P, HTN planning with preferences. I'll cover some of this background and then I'll talk about the contribution of this work, which is the translation from the specialized representation we had called Cascade into more standard representation HTN, and performance improvements we've done for improving performance on these problems for HTN planners. So first, why is stream processing important? It's important for IBM because it's important for IBM's customers, and this is a typical picture of an IBM customer's infrastructure where they have some data sources that are later aggregated and sent to various stores, data marts and warehouses and so on. And one of the issues they face currently is that the delay between the time when data arrives and when you can do something with the data is really significant. And there are now new technologies that help you with that, and one of these technologies is called InfoSphere Streams. It's an IBM product. It's a distributed middleware that allows you to process the information on the fly without storing it, and potentially bring even more information, and that shortcuts the processing. There are customers using this in telco and other businesses. On this platform, you run the applications, as I mentioned, without storing intermediate data, and this is what the application looks like. Just ahead of my presentation, this is going to be the plan for us. One difference from the classical plan execution here is that we don't execute these steps one by one. Instead, we deploy all of them and apply them to a stream of data continuously as the new data arrives. So what this application does, it looks at the feed of trades and quotes from the financial data source, like stock exchange, for example, and computes an average price of a stock over time when it receives new trade information, and it compares it to current quotes and decides whether a quote is a bargain or not. And that happens every time a new trade or a new quote arrives. And what we want to do is we want to compose these applications automatically. We've built a system for this. Our customers have been using it for about 4 years now. But this system is based on a specialized planner, as I mentioned before. So the idea is similar to, for example, web service composition, where the end users want to specify their goals for composition, and the domain experts, in our case, the developers, are specifying composition templates, and the program is put together automatically by using a planner. So how do the domain experts specify their composition templates? This is the approach we developed for them. It's designed to be friendly to software developers, so it would not look like PDDL or anything like this. Essentially, we allow the developers to generalize the application they have by specifying some choice points, different points on the graph. So the question marks here indicate that certain nodes are optional in the graph. The ORs indicate that there's a choice between two implementations, and it's also possible to use abstract nodes that can be replaced by separate implementations defined elsewhere. And each of the choice points can be replaced by another subgraph with another set of choices, so this is a hierarchical structure. We also have semantic descriptions on these components, so each of the concrete components is described semantically. These are essentially strips effects, add effects on these components that let the user specify their processing goal by specifying some of these predicates. We call them tags. For the business users, they look like tags in the user interface. Designing a system like that involves a number of trade-offs, as you of course know. For the end user, we want to optimize the solution in a way that makes sense for the end user. For the domain expert, we want to allow the expressivity that's comfortable for them. We want to keep these both audiences happy. And in the middle, we also have the planner that has to respond very quickly to the requests because the goals are coming in from the user and the user wants to see the response. So the performance is really critical for us. So when we started on this in 2005, 2006, we tried representing this problem in PDDL. It's not exactly the cascade problem. We didn't have cascade there, but a similar problem. The results there were pretty bad, and I don't know exactly what went wrong here. My best guess is that the issue is that when we apply the same component in different parts of the graph, we have an issue with representing the effect of that component, because in different parts of the graph, the output of the component will have different semantics depending on the input that came into that component. For example, if you have an average, an input to the average is temperature, the output is average temperature, input is stock price, the output is stock price. For that, we needed to define a new object every time you apply a component, and that was what made this problem very symmetric and very hard to deal with. So we've built our own specialized planner that knew about this symmetry and solved the problem for us. But moving forward, what we want to do, of course, we want to use more general domain planners. We don't want to incorporate every new development into our planner. That's just is not possible for our small group. So what we want to do is we want to see whether we can translate cascade problems into planning problems. For example, HTN planning problems seem to be a good fit because they have the same hierarchical structure. Can we also improve cascade for our software developers to help them use new expressivity? And this is what we've done. We've translated 7 HTN domains from real cascade problems created by customers. We created about 50 planning problems from that and got good performance. We also solved some challenges in modeling. So what does this translation from cascade to HTN involve? I just will give you a high-level view. So it's pretty easy to see how you can map tags to predicates, composites to methods, abstract components to tasks, and so on. One maybe not trivial thing here is that we have a HTN planner with preferences. So we've modeled the goals that we had in the cascade problem as preferences for the HTN problem. And we also can show that any satisfying flow in cascade corresponds to an optimal plan in the HTN problem. Just quickly to overview some of the modeling challenges. One challenge I mentioned is that there's a lot of symmetry from creating new objects when you apply a new component to new data. And this has been addressed by actually defining a counter. And by the way, we're using SHOP2 syntax here for specifying the effects. The counter helps us only create a new object and helps with some of the symmetry when we need it. Another challenge we had was with representing a tag hierarchy. So in Cascade, there is a way to specify very general goals. So the business user may not care about which visualization to use. They may only care about the result being visualizable. And for that, we can use axioms. This is something that's built into the Cascade specialized planner, but now it can also be expressed for the HTN planner. This is probably what you would expect to define a choice with an optional, like an optional filter, for example. We can specify a choice between two implementations and no op component. And as I mentioned earlier, right, to represent the cascade goals, we are using preferences. So we're saying that we prefer to achieve this goal, and then the optimal solution would be the satisfying plan for the original problem. So moving to how we did computation for this problem, we had this HTN plan P, which was developed by the first author, Shirin Sarabi. We have extended it slightly by adding a new heuristic called the enhanced look-ahead heuristic to take advantage of the additional structure we saw in our problems. This heuristic is general. It applies to any HTN domain. It doesn't hurt to have it, but in our problems it works especially well. And it's basically based on the observation that looking at a particular partial plan, you can estimate what are the additional tasks that are going to be added after the current task. And this is something that could be using a pre-computed index and can be done very efficiently. So that gives us a bound or a way to prune some of the solutions, and that works pretty well in practice. So when we wanted to evaluate the performance, we've used the HTN Plan P planner. In this planner, we've configured it in the following way, so it could use only some of the heuristics or heuristics in a certain order. The existing heuristics that were there, like look ahead or enhanced look ahead, which is the new one, or some combination. And this is a summary of the results. There are more results in the paper. What you can see here is that without the enhanced look ahead, the planner gives pretty good performance, but some of these problems are so large that they could only be solved with the enhanced look ahead heuristic, and having that heuristic really helps in this problem. So to give a summary, this is what we have done. We have investigated the relationship between HTN planning and the cascade specialized planner that we had earlier. We now have the ability to use a domain-independent planner for our problem, and potentially also we can borrow some of the expressivity that this domain-independent planner allows us, and expose that expressivity to our experts, the ones that are developing the domain descriptions, and let them use additional expressivity. We also improved the performance of using our proposed heuristic, which is general but works well for our problems, and we solve very practical problems efficiently.